In this video, we show sequence-to-sequence learning using transformer neural networks. Our sequences will be formed from words of a vocabulary. The words correspond to output nodes in a linear layer. We will use the layer as a sequence generator. The output nodes are assigned probabilities. The one with the highest probability will produce the next word in the sequence. Let's go through an example. Our sequence will begin with the start token. If we process the start token, the generator will produce the first word in the sequence. In this case, the first word is I. If we process the word I, it will produce the second word of the sequence. In this case, the second word is M. If we process the word M, it produces the third word of the sequence. In this case, the third word is fine. Lastly, if we process the word fine, it produces the end token, signaling the end of the sequence. We can construct a correlation matrix to capture information about the sequence generation process. We can say that the start token is predictive of the word I. That is, in our example, I will likely follow the start token. Similarly, the word I is predictive of the word M. The word M is predictive of the word fine. And the word fine is predictive of the end token. One implication on this matrix is that we can mask off the upper off-diagonal values so that we can focus on the forward predictive relationships. Let us store the words of the sequence in an answer embedding and compare it with another embedding. We see that both sequences begin with the start token, but subsequent words are different. The lengths of the sequences are also different. Our sequence generator will need guidance on deciding which sequence to generate given the same start token. We will model this as a sequence-to-sequence learning task by pairing one sequence with another. We will pair the answer sequence, I am fine, with the question sequence, how are you? Similarly, we will pair the answer, yes please, with the question, can I help? Our first attention network will process the question embedding, storing the words, how are you? This attention network will process the question, applying a series of transformations to uncover relationships between the words of the question. We call this applying self-attention on the question. The result is the encoded question matrix. Our second attention network will process the answer embedding, storing the words I'm fine. This attention network will process the answer, applying a series of transformations to uncover relationships between the words of the answer. This is called applying self-attention on the answer. The result is the encoded answer matrix. Our third attention network will process the encoded question matrix and the encoded answer matrix. It will uncover relationships between the words of the question and words of the answer. It will use the relationships that it finds to guide the sequence generator. In this case, it guides it through one vector at a time to generate the answer, I am fine, in response to the question, how are you? The attention network uses linear layers to learn weights that reflect these relationships. This enables the network to predict the next word in the sequence. Because our attention network has multiple heads, all the operations we've discussed send input to our sequence generator. Now, let's look inside the first attention network and see the self-attention performed on our question embedding. The embedding stores the words, how are you? These words are tokenized, projected with a linear layer, and position encoded. The results feed into three linear layers. The layers will compute three different projections for the question. These projections are coined query matrix, key matrix, and value matrix. The first and second projections of the question will be dot product to obtain a score matrix. The The score matrix estimates potential correlations between pairs of words in the question. Here we find high correlations between the pairs how and are, how and you, and are and you. In practice, we apply normalization and softmax on the correlation values for numerical stability. We will dot product the score matrix in the third projection of the question. The resulting encoded matrix encodes the words of the question and captures estimated relationships between pairs of words in the question. These dot products are occurring in different attention heads, so we use another linear layer to allow the results of the different attention heads to interact. The last layer, a fully connected layer, explores other potential correlations in higher dimensional space before it produces our encoded question matrix. Let's look at the second attention network and perform self-attention on the answer embedding. The answer embedding stores the words "I'm fine." These words are tokenized, projected with a linear layer, and position encoded. The results feed into 3 linear layers. As before, the layers will compute 3 different projections for our answer. The first and second projections will be dot product to obtain the score matrix. To enhance the network's ability to generate answer sequences, we will mask out the upper off-diagonal values. The score matrix estimates potential correlations between words of the answer. Because our network needs to generate an answer sequence, the masking will ignore correlations that are not useful for forward sequence generation. Here we apply normalization and softmax. We will dot product the score matrix in the third projection of the answer. The resulting encoded matrix encodes the words of the answer and captures estimated relationships between the words of the answer. As before, we allow the different attention head results to interact with another linear layer. And we use a fully connected layer to explore potential correlations at higher dimensional space. Here we get the encoded answer matrix. Lastly, let's look at the third attention network, where we process the encoded question matrix and the encoded answer matrix. The encoded answer matrix will connect to 1 linear layer to produce projection 1, and the encoded question matrix will connect to 2 linear layers to produce projection 2 and 3. Projection 1 encodes our answer, while projection 2 encodes our question. We will dot product the 2 to obtain the question and answer score matrix. The score matrix estimates potential correlations between the words of the question and words of the answer. Here we estimate high correlations between the words how and fine, between the words are and am, and between the words I and you. Again, we apply normalization and softmax. We dot product the score matrix in the third projection, which is the second question projection. The resulting encoded matrix encodes the words of the question, as well as the estimated relationships between words of the question and the words of the answer. As before, we allowed the different attention heads to interact using another linear layer and a fully connected layer to explore other potential correlations at higher dimensional space. Here we produce our final output matrix. Our final output matrix will connect to the sequence generator. Because our output matrix encodes words of the question and all the potential relationships with words of the corresponding answer, our sequence generator is presented with all the information it needs to generate the corresponding answer sequence. Here we process the first entry of the output matrix. The sequence generator will produce a probability distribution and predict the first word of the answer that follows the start token to be the word I. If we process the second entry, the sequence generator will predict the second word of the answer to be M. If we process the third entry, the sequence generator will predict the third word to be fine. During training, softmax will be applied to the output values of our generator. The resulting probability distribution will be compared with that of the training data. The KL divergence function will provide a measure of how different the resulting probability distributions are from the training data's distribution. This will deliver the gradient signals necessary for the network to adjust weights in all the layers of the network to enable sequence-to-sequence learning. This concludes this video. Thanks for watching. See you soon.